one major question in your final. Alright, so if the block is deviated by distance h, and gravity acting on the block is Fg, then the increase of potential energy will be the minus of the work done by the conservative force here, which is gravity. And the work done by gravity in this case will be positive or negative?
Negative.
Good. Because it is pointing in the opposite direction as your box's displacement. So it will be negative Fg times g, which is positive. So you see your potential energy increase, which makes sense. And this increase of energy comes from the work done by the man here. If the force applied by the person is making an angle, and we call this angle between this lever arm, we call this distance between the pivot to the point that the force is applying as lever arm, which is R2. So the lever arm for gravity is R1, the lever arm for this force is R2. Okay? And we extend the lever arm and call the angle between the lever arm and the force as theta. Now, there are two components. One is the component for the force along the displacement. One is the component of the force perpendicular to the displacement, but points toward the direction of the lever arm. Should I take when I'm computing the work done by the person, should I take the displacement, should I take the component along D or perpendicular to D? Along D or perpendicular to D?
Along D.
Good. So if this is theta, will this be F sine theta or F cosine theta? Sine, good. So the work done by the person will be D times the sine theta of this force. I know in work, you end up being F times displacement times cosine theta, is because that definition of angle is different. In your work formula, the angle is defined as the angle between displacement and force. But for rotation, the lever arm is important, so we define the angle with respect to the lever arm. So that's why it becomes sine. But you are still taking the component along the displacement. You need to have force along the displacement to work. And you need to have a component perpendicular to the lever arm in order to rotate this seesaw. Alright, so this force causes this change of energy. Work equals the change of energy. Work is dF sine. Change of potential energy is FGH. This G is small. So you get D is R1, R2 theta. H is R1 theta. And now you can cancel the theta because they are the same on both sides. I should call that a different name. So let's call this delta theta. Delta theta, which means the angle that it rotates. Just so I don't confuse that with this theta over here. But anyway, it's going to be cancelled. Yeah. Okay. So at the end of the day, we see that the criteria for rotating the scissor and lifting up the box is R2 at sine theta, and that equals to the force from gravity times the lever arm. Yeah?
How come the forces don't cancel?
Because one is gravity, one is your force.
Okay.
The force you apply doesn't need to equal the force on the box. And in fact, you see that they shouldn't, because they are multiplied by the lever arm, which is not equally long. This is shorter, this is longer, and you also need to consider the angle that the force made with the lever arm, because only the perpendicular component can input energy into the system by doing work. And therefore you have this factor of sine, and work is related to displacement, so the longer the lever arm, the bigger the displacement. And of course the force itself affect, but it's not the only thing affecting this motion. You need lever arm, you need force, you need to take the perpendicular component, and that's the criteria for lifting up this box. Okay? So, if the lever arm here is longer, does it require bigger force or smaller force?
For R2?
So yeah, so for R2, if we make R2 longer, does F becomes bigger or shorter?
Smaller.
Smaller, good. So that's how you can lift up a really heavy object with a long lever arm. You just need a divot. Yeah, that's pretty easy. I can even make the lever arm longer. You see, just this small thing can lift out that picture. Because when you are doing rotation, the energy conservation force, the relation becomes the lever arm times force equals lever arm times force. It helps you to reduce the force in need because the distance you need to move is longer. And the energy you input is always the same. So the longer you move, the smaller the force you need. Okay? Have you guys learned this before? Lever arm? Really? No? Well, it's like the most useful thing you will learn. That's how you move heavy object. If you are a student, you need to move a lot, and that's how you move heavy object. Okay, so we see that the thing controlling rotation is not force. It is this combination between the lever arm, the force, and sine theta. So we call this combination torque, and we use tau, a Greek vector, to denote torque. Right? So if you have a object, any object that is rotating around some pivot, you want to look at how will it rotate, and you have a force from here, let's call it F1. If this force is acting on this point, then the lever arm of this force will be this long. Okay? And then the angle between the lever arm and the force will be this angle. And the torque caused by the first force, F1, will be R1, F1, sine theta 1. Okay? Now, if I have another force acting like this, then the lever arm becomes here. And the angle between the lever arm and the force becomes bigger than 90, but that's totally fine. You can do sine theta with theta bigger than 90. You guys know that? Try your calculator, it will give you the correct answer. The way sine is defined is by drawing a circle. When it is smaller than 90, it becomes the y position divided by the radius. Right? The y position is this long. When you are at the other side, it is still y position divided by r. So for sine theta, it is still positive when you go over 90 degrees. That's the definition of sine. And it will take you to the perpendicular component of this force. So you are still calculating the work done by the force correctly. So just always take the angle from the lever arm to the force. Okay? So here, the torque caused by the second force will be R2 F2 sine theta 2. Now, which direction will F1 rotate this object? Clockwise or counterclockwise?
Clockwise?
Good. How about F2?
Counterclockwise?
Good. So this torque is rotating the object in different direction. Torque has direction. It has clockwise or counterclockwise. And usually we are right-handed. So when you use your right hand and point toward the direction of rotation with your four fingers, a counterclockwise torque